Swayam Prabha. Digital India. Educated India.
Multi-chain polymerization, what is the necessity of this multi-chain concept of multi-chain polymerization? What is the meaning of this multi-chain? If you prepare a polymer using some bifunctional monomers, two bifunctional monomers, you will get a polymer system having only two ends of the polymer chain, and that is termed as exclusively linear polymer, or little bit branches may be there, but if it is exclusively bifunctional and strict stoichiometry is maintained, then it will be exclusively linear polymer. But along with some bifunctional monomer, if you take a trifunctional monomer or a tetrafunctional monomer, then the polymer product which is obtained from that polymerization will no longer remain as a linear polymer. The polymer molecule will contain more than two ends, more than two chains. That is why it is called multi-chain polymerization. Am I clear? Now, for the sake of calculation of the amount of reactants to be used for such polymer synthesis, we have to consider the average functionality, average number of functional groups present in the reactant system we have taken. Say for example, if you polymerize phthalic anhydride and glycerol, what is the formula of phthalic anhydride? Okay. Plus this is a trifunctional monomer, here F is equal to 3, here it is a difunctional monomer, here F is equal to 2. Now, this phthalic anhydride, it is anhydride devoid of water. Now, if you add water to this compound, this anhydride ring will open, forming two carboxyl groups. So, in effect you will get glycerol is an alcohol, trifunctional alcohol, triol. So, this will condense, this will also condense, this is primary hydroxyl group, secondary hydroxyl group. So, what will happen? As I showed, so if you consider this as a BB having two B functional groups with A functional groups, trifunctionality like this. So, you will get a polymer system like this branch. Now, the end of this branch or this polymer chain ends may contain again OH or That means a mixture of carboxyl and functional groups at these ends of these polymer chains. They are further reactive. It can react with another species of this kind. So, what will happen? It will continue to grow bigger in size. So, this is a branched structure. And this branch structure will lead to, since those groups are reactive, as I told, hydroxyl and carboxyl reactive groups are there in their ends. So, they will lead to intermolecular cross-linked network structure. These are linked by primary valence bonds. This is a planar network structure. We can draw a 3-dimensional network structure I showed you earlier. So, this is a cross-linked three-dimensional network structure. This polymer structure is insoluble in any solvent and also infusible by heat. Do you understand? So, we must have to have a control over such type of growth of polymer structure. Once this kind of structure is formed during the polymer synthesis, that polymer mass can no longer be used for processing as well as leading to a finished product. So, what you have to do? You have to stop the polymerization at the branch level like this. You have to stop the polymerization here, because each of these ends are reactive. You can consider this as a pre-polymer. I give you a concrete example of phenol formaldehyde resin. There are two ways of phenol formaldehyde resin synthesis. First day I told you, I showed you how phenol and formaldehyde condenses. A stage resin, do you remember? A stage resin, B stage resin, C stage resin, of which A stage is linear and soluble, thermoplastic. B stage is branched, soluble, still it is thermoplastic, and C stage is the final stage, a cross-linked thermoset stage. So, we have to stop the polymerization at the B stage. Maximum you can go up to the B stage. Then you take that B stage polymer for making any laminate, for making any composite. So, for making a glass fiber reinforced phenolic resin composite, which is a FRP, fiber reinforced plastic. What is done? You have to synthesize phenol formaldehyde resin up to B stage. That B stage polymer, you take B stage phenolic resin, soak this B stage phenolic resin into a glass fiber mat or fabric, then you will get glass resin impregnated PF resin impregnated glass fabric called a ply, one ply. You take this 3 to 4 plies of PF resin soaked glass fiber cloth, assemble those 3-4 plies together, then apply heat and pressure. Heat means the temperature should be say around 150 degree Celsius. You will get a glass fiber reinforced phenolic resin composite. Do you understand? So, this B stage resin can be considered as a pre-polymer. Up to pre-polymer stage, the polymers remain soluble and fusible. That polymer should be used for product fabrication, product processing, and final fabrication, final shaping, final fabrication is given by applying heat and pressure, where some chemical reaction occurs at this stage. Which is known as cross linking, and the morphology will be a 3-dimensional network as I have mentioned. And the cross link density of this kind of polymer system will depend on how much cross linking agent is used or how much reactive functional groups present in the B stage resin. Cross link density I means the number of cross link bonds, intermolecular cross link bonds present in that system, or other way around we can say what is the length of the polymer segment between two cross links, molecular weight of the polymer segment between cross link. That way you can also express the cross link density. So, this kind of system a situation can be understood taking account of this calculations, and a pre-polymer should be prepared considering this critical extent of reaction. Then only it will be a useful polymer for fabrication of a suitable product, otherwise that batch of polymer is to be discarded. That will be total wastage. Understand? So, this is what about the condensation polymerization or step reaction polymerization leading to polymers like polyesters, polycarbonates, polyamides, polyimides, polyethers, like this. This is the principle I have described in brief before you. You please go through books I have referred and please solve numerical problems given as exercise problems at the chapter of end of the chapter of those books. Okay. Now, let us pass on to radical chain polymerization or chain polymerization rather, or polymerization by addition chain reaction principle. Condensation polymerization principle is reaction in steps, that is why that was a step polymerization, and you have seen the characteristics of step reaction polymerization. Now, you will understand the characteristics of radical chain polymerization or addition chain polymerization. Then you can compare the characteristics of step reaction polymerization and addition chain polymerization. Now, in case of condensation polymerization, you have seen that minimum requirement for the reactant molecules to be polymerized are bifunctionality. The reactant should be bifunctional, at least should be bifunctional. In case of radical chain polymerization, we must have such type of consideration, although the monomers which undergo addition chain polymerization do not contain such type of functional groups. What are those things? That compounds are available like ethylene, propylene, butadiene, isoprene, vinyl chloride, methyl acrylate, methyl methacrylate, acrylic acid. So, each of these compounds contain an olefinic unsaturation or a double bond in the molecule. These are organic molecules and they contain some double bond, olefinic double bond. Now, that olefinic double bond supplies this functional site for linking up with one another, forming a large molecule, macromolecule. So, here certain considerations should be discussed for polymerizability of such olefinic monomers. You know, for any reaction to happen, it must have certain thermodynamic feasibility. Once the thermodynamic feasibility is achieved, then we must also consider its kinetic feasibility. That means, rate at which that reaction occurs to produce a polymer. What is thermodynamic feasibility? That free energy change should be negative. For any process, if the free energy change is negative, then only that process can happen, that chemical reaction process or chemical synthesis process can happen. Now, let us look into these monomers which undergo radical polymerization or addition chain polymerization. Radical polymerization, I mean polymerization involving free radicals, single electron free radicals available in the monomer that can undergo polymerization. If in this monomer some free radical is available, that free radical will interact with a monomer to generate a free radical, then that will lead to couple forming a bond. How? I am showing you. Suppose you take a compound, say represented by R R. This is a bond. In this bond, there are 2 electrons involved. Now, if some agency can break this bond, say maybe heat, maybe electromagnetic radiation, or maybe some chemical agency, if their energy, if the energies of those agencies, heat, thermal energy or electromagnetic radiation energy or chemical energy, if their energy is more than this bond energy, energy of this bond or bond dissociation energy, then only it can be broken. So, if that is sufficient, then it will lead to form 2 free radicals like this, 2 R dot, provided these 2 electrons shared by each member are cleaved homolytically. That means, each of them will take their share, equal share, that is called homolytic cleavage. Now, this is highly reactive, this radical is highly reactive. Now, if that radical comes in contact with a monomer like this, or you can visualize this way. What will happen? That will initiate to open this pi bond, forming a bond with this monomer molecule, leaving behind a free radical at the end of this carbon. That means, 2 electrons present in this pi bond, one of those 2 electrons will be used by this radical to form a bond like this, and another radical will be created over here, it will be remain there. Now, this species is highly reactive. So, it will further initiate or further add to another monomer like this. So, this process continues at a very fast rate, and ultimately what happens? If this process continues, allowed to continue, ultimately we can get actually this is not the right way to show anyway. Suppose this is N. Now, this situation let us examine where this kind of situation can happen. Let us examine. You look at this monomer, it is a vinyl monomer where this unsaturation is present. Now, this is a ketonic group, C double bond O. That means pi electrons are present over here. Now, these kind of molecules can undergo chain polymerization. How? I have shown over here. Now, I told you the agencies here, these agencies or this free radical, what will be the nature of this free radical, so that they can attack these molecules to form a free radical like this. How it happens? You see, here is a double bond between a carbon and an oxygen that can polarize. That means, the incoming agency that may be heat, that may be electromagnetic radiation, that may be a chemical species, that will disturb the pi electron between this carbon and oxygen or carbon and carbon. It will disturb in such a way that it can either polarize, forming a positive center as well as a negative center, positive center on carbon, negative center on oxygen, depending on the electronegativity of the atoms present there, or in this case also it can polarize depending on the substituent present over here. I will show you later. Either this can be broken homolytically, producing two free electrons, one over here, another one over here, or it can polarize like this, forming a cationic center and an anionic center. So, perturbation of this pi electron depends on the incoming group, incoming agency, which will attack the molecules like ethylene, propylene, vinyl chloride, etc. Then it will continue to add on to each other. Here you look, effect of substituents. As I was telling you, now this is the monomer, olefinic monomer having this pi bond. Now, if some initiator comes close to this monomer, that can polarize, forming a positive center and a negative center, polarization of the pi electron, pi bond, or it can break into two free electrons, a homolytic cleavage, heterolytic cleavage. That depends on, look at here, suppose a Y substituent attached to this carbon. Now, if this is electron, if this has a capability of electron donating nature to this pi electron, so that will increase the electron density in the pi bond between these two carbon, or else it can decrease the electron density by withdrawing electron. I mean to say that this group may be of that makes the monomer its polymerizability. So, you can say, sir, what is the necessity of thinking or taking into concept this concept? Yes, there is a necessity. If you want to design a new polymer, if you want to design a new polymer, if you want to synthesize a new polymer, novel polymer which is non-existing today, then you have to start with a monomer. What kind of monomer you should take? For that reason, say if it is of addition chain polymer, you think of a substituent which is electron rich, which can donate electron to this system. If it donates electron to this system, to this region, so this pi electron cloud will be polarized. So, here you see in this example, this Y group is electron donating in nature. So, what happens? So, electron density on this carbon will be more. So, it will be delta negative and this side will be delta positive. So, this is the monomer, this is the monomers, this is the inherent nature of the monomer. Now, we think of the attacking species, attacking initiator. If that attacking molecule comes close to this, which is of electron accepting type or electron donating type, then that can further polarize or that can attach to this molecule. Okay. Once this happens, it can polarize and this electron will be again delocalized by these resonance structures, resonating structures. Again, this is necessary because it needs to be stabilized. Once this is polarized and some attacking molecule is coming to change its character to start the polymerization, then it must have sufficient stability. Suppose somebody has entered this room to attack you, okay, for stabbing. Now, if you run in this room at a very high speed, you will not be able to do it, but if he is little stable, becomes little stationary, then he will find you at some place and he can easily kill you. It is like this. So, stability. So, stability of this is an intermediate. The stability of this intermediate should be a parameter, should be a criteria. Otherwise, you cannot get a polymer. If it is very unstable, its existence will not be there for attacking with another or reacting with another species. What is that group? Electron donating type. Say you think of a methyl group. Think of a methyl group is electron donating in nature. That will increase the electron density. If it is methyl group CH3, that will increase the electron density over here. So, this is a case of propylene, or you can take a case of isobutylene. In propylene, one methyl group, in isobutylene there are two methyl groups. So, that will further increase the electron density in the pi bond. So, this way we have to see an agency which is coming to attack this molecule, whether it will break the pi bond homolytically or heterolytically, that depends on the substituent present or substituent attached to that carbon or to that molecule, or the nature of the attacking species, whether that is of electron donating type or electron withdrawing type. That way we will see, and we will get free radical polymerization, cationic polymerization and anionic polymerization. Free radical polymerization means it is a polymerization initiated by a free radical, Cationic polymerization means it is a polymerization initiated by some cationic species, say some Lewis acid, say boron trifluoride water combination, that undergoes cationic polymerization, or sodium alkyl, some metal alkyl, that will cause anionic polymerization. In case of acrylonitrile, here you see in this case this CN group is electron withdrawing type. It is withdrawing electron from this pi bond. So, this carbon will be delta positive. Okay. This kind of monomer will undergo polymerization by anionic species. Say butadiene will be polymerized, can be polymerized by anionic species, anionic polymerization. Isobutylene can be polymerized by cationic species, cationic polymerization. Okay. So, this is the situation. Radical species are neutral, you know, and do not have stringent requirements for attacking the pi bond or for the stabilization of the propagating radical species, and resonance stabilization of the propagating radical occurs with almost all substituents. Resonance stabilization means the intermediate or the radical species, monomeric radical species which has been formed after initiation, that should be stable enough for growth of the polymer. Okay. Now, modes of propagation. You look into this monomer, olefinic monomer. To one carbon, two different groups are attached, and to other carbon only hydrogen atoms are there. Now, how they will attach with each other? This is a kind of growth, or it can so happen that if you consider this as head, this consider it as tail, then this kind of combination during the propagation of the monomers to form a polymer, that is known as head to tail addition. This is head to head addition, or else you can get this is tail to head to head, tail to tail, head to head. Sorry, head to tail. When it will happen? Shift of charge or this radical addition, that is different thing, but here you have to consider the steric aspect. Steric aspect. Now, if that depends on the size of these substituents. So, bigger groups will hinder for this kind of addition, bigger substituents will hinder this kind of addition, whereas that will augment this kind of head to tail addition. So, that depends on the size of the substituents present in the monomer structure. Now, let us see the sequence of events that occurs in radical chain polymerization. Now, there are again we must say some steps can be identified as initiation, propagation, termination of polymer growth. So, in the sequence of synthesis of a polymer from a monomer by addition chain reaction principle, it needs an initiator system to initiate the polymerization of an olefinic monomer. Once an olefinic monomer is initiated by a initiator molecule or initiator radical, then it propagates that addition reaction, propagates further addition of monomers to build a very long chain molecule. Now, there must be a limit of chain growth, limit of growth length of the chain which is formed during such polymerization. In order to control the molecular rate, to what extent it should continue, that is say 10,000 molecular rate or 5,000 molecular rate or 10 lakh molecular rate or 60 lakh molecular rate, where we should stop. That means, you have to terminate the polymerization at the final step, termination. Let us take a peroxide molecule. You know, these peroxide molecules are unstable molecules, because this bond is thermally less stable. So, if it is heated, say at 50 degree Celsius temperature, it will break into free radicals like this, 2 Ru radicals. This is a free radical formation reaction. Here this ROOR is an initiator. RO is an initiator. A typical example of this initiator may be benzoyl peroxide. What is the formula of benzoyl peroxide? Is it okay? BPO molecule, or you can have some hydroperoxide, say cumene hydroperoxide, yes, isobutyronitril, AIBN, azo-bis isobutyronitril. That azo bond, nitrogen double bond nitrogen, there is unstable, that will break into releasing a free radical. Hydroperoxide, this hydroperoxide can be cumene hydroperoxide or dicumyl peroxide. So, these are known as free radical initiator compounds or molecules. Now, this initiator molecule, if that is designated by this I initiator molecule, that decomposes thermally. So, temperature might be 50 degree, 60 degree, 70 degree, 75 degree, 80 degree. Their decomposition temperatures are different for these compounds and they have certain half lives. Okay. So, once this initiator decomposes into homolytic decomposition of that initiator forming R free radical, that R free radical will add on to a monomer designated by M. That monomer may be ethylene monomer, may be methyl acrylate monomer, may be methyl methacrylate monomer, may be a vinyl chloride monomer, may be an acrylic acid monomer, like that, where you will have a double bond like this. This is a monomer. So, it forms a monomer radical. Initiated radical initiates a monomer to form a monomer radical. So, this step is known as initiation step. This is initiated decomposition step and this is initiation step, and both this decomposition and initiation are included in this initiation step. Then propagation of the initiated monomer radical to intermediate growing chain radical. Here, after this first monomer radical reacts with a second monomer, it will, the length will be doubled here, and this is a growing chain radical, and like this it will continue to add more and more number of monomers, M3, M4, M5, M10, MP, MQ, Mn, like this, depending on the number of monomer molecules added to this growing chain. These are all growing chain. Now, their stability, I was talking of their stability, the stability of this free radical are maintained by forming resonating structures through hyperconjugation. So, they are reasonably stable for the attack of a monomer molecule or attacking another monomer molecule. That means, these monomer molecules are coming vicinity, coming close to this growing chain, and it is added. So, gradually it is increasing, and entire this step occurs at a very first rate. If you look into the rate constant data, you will see how fast it is. Then all these steps, intermediate steps, are known as propagation steps. Okay. okay, overall propagation of monomers to growing chains. It is not that only one chain is initiated and only one chain will be formed, one growing chain will be formed. Here only a case of one initiation is shown. Now, in that system there are more number of initiator molecules. In a typical polymerization of a vinyl monomer, say methyl methacrylate MMA, here initiator used say 0.1%, 1 to say 2% initiator concentration is used. That means, if you take benzoyl peroxide, how much benzoyl peroxide has to be taken? Say if you take 100 gram monomer, so you can take 1 gram of initiator or 0.5 gram of initiator, like that. Okay. Now, that 0.5 gram initiator, how many molecules are there? So, few of those molecules will break initially, so if not all at the same time, or slowly it can break depending on the availability of your bond breaking energy from the thermal source. So, simultaneously there can be large number of initiator molecules decomposed into free radicals and large number of initiated monomer will be formed. Okay.
Step is a rate determining a step.
Please wait for some time, keep your patience. Okay. First you see, this is the initiation step, this is the propagation step, propagation continues. Then these radicals are live, these growing chain radicals are live. Live in the sense they have the capability of adding more monomers. If there are monomers available in the reactor, in the container, it will go on continuing the addition of the monomer till it becomes dead. This is a live radical, these radicals are live radicals, these are not dead. Now, in order to kill these growing polymer chains, they need to be terminated, their growth needs to be terminated. Now, that termination occurs by two ways. Now, in the system there are many growing chain radicals. Okay. Now, this is one growing chain radical represented by Mn dot, means n number of monomer molecules are there in the chain, n may be 5000, value of n may be 5000. At one end there is a free radical. Similarly, you can have another chain bearing this free radical at one end having m number of molecules. So, you can visualize this way. Suppose this is Mn dot, this is mm dot. These two radicals can couple.
So, the activity of both radicals will be same.
I am keeping your question in mind, I will explain later. Here these two radicals couple forming a covalent bond, because two free radicals can react. So, in effect what we are getting, so these are this is a dead polymer molecule. it is no longer capable of adding more monomers to it, it is dead. Their radical or growth activity is annihilated, stopped or terminated. This kind of termination is known by termination by coupling of growing chains. Now, there can be another case where two growing chain radicals can disproportionate interact through disproportionation for stopping their growth activity. How that occurs? If I show this way, showing only one monomer unit at the end of those growing chain radicals, what can happen? Now, this species, say suppose this is dot, this is dot. This dot can abstract one hydrogen from this carbon. So, what will happen? If it does that, it will be CH and here one radical will be created. So, a pi bond will be created over here and there is no longer any free radical present, and in this case what will happen? This species has taken this hydrogen from here. So, that hydrogen radical, hydrogen means not hydrogen atom, hydrogen radical that looks like that, this C H So, if it breaks, it will form, I am sorry, and one hydrogen will be, hydrogen radical will be formed. That hydrogen radical will react with this one, forming CH3 CH2 CH3 CH2. Okay. Now, look at the peculiarity. In this case, this species becomes saturated, this species become unsaturated. Here the length becomes doubled. If they are of same size, here the length of the polymer chain remains equal to the length of the growing chain. This is known as termination by disproportionation. So, there are 3 steps: initiation, propagation and termination in this polymerization, addition chain polymerization. Thank you very much.